Coulomb's law. Experimental observation shows that opposites attract and sames repel, right? So you've heard this before. Charge comes in two varieties. For example, an electron has negative of a fundamental charge and a proton positive of the same fundamental charge. So the idea of there being plus and minus charges is well known from other subjects like chemistry. So opposites attract, sames repel. And the empirical formula for the magnitude of that force is that the force is proportional to the product of charge over the distance between the charges squared. So K Q1, Q2 over R2, over R squared, sorry. K is the Coulomb constant, 8.99 times 10 to the ninth in our MKS units, which would be Newton meter squared per Coulomb squared. Again, all these fundamental constants and units are on the formula sheets. So at this point, we just take the Coulomb's law as empirical. And before we go further with electric field, it's nice to do a problem or two. So the examples we'll try right now involve an equilateral triangle where there are 3-point charges, and we'll do 3 separate problems. In each case, A, B, C, we will want to get the total or net force acting on a particular charge. And I've listed the answers here, so if you'd like to first see if you can get these results on your own from your knowledge of vectors from Physics 1. Otherwise, we'll continue on and we break it down. So in this example, we have 3 charges, and we want to find the force that acts on the minus 4 microcoulomb charge. Right? So it's often nice to think of it as you are here, right? You're at the what we would call the object of interest, right? And that makes the minus 2 microcoulombs and the plus 3 microcoulombs charges in the surroundings, right? So let's, our first example here will be to find the force acting on the minus 4 microcoulombs. So how we do this is by what's called superposition, because the formula we had, F equals K, Q object, Q1 over R squared, that's really just a formula between 2 charges. And also, when we discuss vectors, it's a force magnitude, right? So what we do for superposition is to say, well, the minus 4, right, are acted upon by the minus 2. So minus, that's like charges repel, right? So if we call this one Q1, and we are Q object, and this one is Q2, right? Then we can label this the force of 1 on the object. I'll just write it F1. And then we have F1 is K Q1 Q0 over the distance squared. Now notice I changed centimeters to meters. I didn't yet change microcoulombs to coulombs, but we will have to do that. Micro is 10 to the minus 6. Also notice that I did not include the minus signs in the charges for the force formula. And that's because we're going to learn that vector formulas are almost always formulas for magnitudes, with a couple exceptions. So it's implied that the formula actually is an absolute value. And it's on us to get the arrow direction and do a force diagram with arrows, okay? Secondly, then we have Q2 is positive and the object is negative. That's attract. So we want to attract to the positive, right? So we would have F2, right? And F2 is just K, 3 micros, 4 micros, right? KQQ, right? You know, the product of the 2 charges over the separation distance turns out to also be 0.2 meters squared. And then we would then have to add vectors. Now, when we do this, I'm just going to show some results. I'm drawing a little smiley face at the object of interest, and I've, again, the Q1 is the -2, and the Q2 is the +3, and we are Q object, right? So F1, the force that the -2 exerts on the -4, we said was here, right? So I'm just showing it in a little better diagram, right? So F1, when we calculate the magnitude KQQ over R squared, you should get 1.8 newtons. F2, again, we said before, minus plus attract, right? So F2, and again, I'm showing it here. F2, you should get 2.7 newtons. Now, also, the gory details of vectors is that you'd have to know something about the geometry. We had an equilateral triangle, right, where the angles are all equal and 60 degrees. So then we'd have all the details of, getting the components of F1, for example. We would, make the F1 arrow the hypotenuse of a triangle. And so F1x, right, in the fx column is F1, which is 1.8 times cosine 60, and that gives us 0.9. And then the y component is 1.8 sine 60, and that'll give us about 1.56. Similarly, for the 2.7, we sort of make a triangle here and look at, the F2 being the hypotenuse of that triangle, and the components are basically the legs of the triangle. Although being careful of quadrant, right? Like, quadrants go at 1, 2, 3, and 4, right? So F1 is in quadrant 1. It has both positive x and positive y components, but F2 is in quadrant 4, right? So it has positive x but negative y. So that has to be taken into account. So 2.7 cos 60 is 1.35. 2.7 sine 60 is 2.34, but quadrant 4, we want that negative, so minus 2.34. We add our x components, we add our y components, and then we get magnitude and direction of the final answer. Now, I'll talk a little more about vectors in a minute, but it'd be important for you to fully understand how I'm calculating these magnitudes, how I'm getting these components. For each vector, how I'm getting the so-called direction, the standard angle. For example, F2, standard angle is from positive x counterclockwise over to the vector, right? So that would be 300. I knowing what quadrant it's in. And this angle delta is like the acute angle in the right triangle, right? That was, for F2, it was 60. Right, so the direction's 300, but in a little right triangle, it's 60 degrees, right? So, and then to get the resultant, which I show in a separate diagram, this diagram's getting very messy now, but you can also think of the parallelogram method. You just sort of picture F1 added to F2 or F2 added to F1, and that gives us this result here, and I just drew it separately. And so again, you need to know how to get these components and then this magnitude and direction in this kind of an example. But we'll do more examples, right? This is just the first one. So right at the start, you have what seems like a simple formula, Coulombs Law. And the very first example we do has more than 2 charges, so you have to understand superposition. And force is a vector, so you have to understand how to deal with vectors. So we'll do more of these, right? Here's the same setup from the problem A that we did. The same 3 charges, the same geometry, but now calculate the force acting on the 3 microcoulomb charge, right? So you should now think about you being at the location of the +3, right? And I always like to draw either a stick figure or a smiley face, so I know where I am, right? And I can think about attracting to the -4 and attracting to the -2. So that would be the arrows you would draw. You would calculate the magnitudes of those arrows, do an arrow diagram and figure out the components, and end up getting magnitude and direction of the answer. So please do that and see if you get these results, right? So again, here's the smiley face, meaning we are here. If we call Q1 and Q2, the -2 and the -4, we are always the object, right? Then see if you can calculate the magnitudes of F1 and F2, the components that you would get, understand what their directions are and what quadrant they're in. Notice F1 is actually not in a quadrant, it lies on the negative x-axis, right? And then when you combine your x components and y components, see if you can get the magnitude and the direction of the final answer, which I'm showing you is in quadrant 2. And so give that a go. Then we'll do the same thing, and now we'll just say that, we are here, right? We are the -2. Let's find the force acting on the -2. Go through the same analysis of doing your arrow diagram, getting the components of the F1 and F2. Let's call Q1 the -4 and Q2 the 3. And again, we are always the object. So do your arrow diagram, get components, combine x and y components separately, get magnitude and direction of the answer. And we should, you should come up with this. So again, here's the diagram, here's the smiley, meaning that's where we are. See if your arrow diagram looks something like this, and if your resultant sum of the superposition of the forces F1, F2, indeed gives you these components and this magnitude and direction in quadrant 4. And again, delta is the angle, the acute angle in the right triangle. Direction is the standard angle, at least for now. That's, the standard way of doing it from Physics 1. Okay, so good luck with that. We'll discuss when we're live.